All right, welcome to unit number 4 on conservation of energy, lesson number 5, conservation of mechanical energy. So in this first example, we have a setup of a pendulum here. But before we dip into that, I'm going to give you a quick little overview of what conservation of mechanical energy even means. So in short, basically, mechanical energy means that if there's no friction or there's no work being done to our system, which we haven't really got to too much yet, um, the total amount of energy is going to remain the same at every point. And so we can say that energy mechanical initial or before, people often make better sense of it when I write before, is equal to energy mechanical after. And the book likes to put energy total initial is equal to energy total final. That works as well. Essentially what they're talking about, and we're going to be mainly using 3 types of energy here. Well, 2 types. It's going to be potential and kinetic. There's going to be 2 potentials. There's going to be energy potential, and we're going to be using due to gravity, plus kinetic energy, and there's also going to be some spring energy in here as well, but that also falls within the potential energy category. Anyways, all of these before, so maybe I'll put a little initial beside all these, is going to equal the sum of them after as well. They'll just be in different ratios. So we can say EPG final plus EK final plus ES final. All right. So essentially what we're saying is that the total energy in frame A, so maybe the before situation is going to equal all of the energy in the after situation, except things are going to change places, which means their energy values are also going to change. All right, so with that said, let's jump into this problem. The problem says the mass on the end of a 1.8 meter long pendulum has a maximum speed of 3.75 meters per second. We want to determine its maximum height. All right, so how do we go about doing that? Well, we're going to use this formula. Mechanical energy before is equal to mechanical energy after. And actually, it's quite easy. I'm just going to pick up with this formula and start crossing some terms out. The maximum height of this pendulum looks like, in this case, it is the before situation. We know that our pendulum string's 1.8 meters long. That's not totally what we're looking for. We're looking for how high this pendulum is off the ground. So right here, that is our height value that we're looking for. Okay, so I'd assume also at max height, this pendulum is at rest. It's not moving, so it has no kinetic energy. That said, let's start crossing some terms out here. We're going to use this expanded out formula that we already have. There's no springs in this situation, so let's get rid of these springs right away. There are also no... Well, let's look at the before situation. Before situation, this is at rest because it's at max height. So there's no kinetic energy because kinetic energy would require velocity, right? Formula for EK is 1/2 mv squared. So let's cross out initial kinetic energy. But if there's height and there's mass, that means we have potential energy. Now a little note that we don't see mass here. Don't worry about it yet. That's the trick of the question. All right, so we have energy potential due to gravity initial here. So let's simplify this down and move this over here and say EPG initial, that's our only energy source initially, is equal to, well, we haven't finished crossing these out. When this bob gets to ground level, it no longer has any potential energy. Its height is effectively 0. So for potential gravity final, that one's going to be 0 because there's no height. But the kinetic energy, this now has a velocity of 3.75 meters per second, which means we have kinetic energy. So we'll call this energy kinetic final. All right, so far so good. Now all we have to do is expand these formulas out even further and put numbers in and solve. So energy potential initial, we're going to have mass times gravity times height initial is equal to 1/2 times mass times velocity squared, and this is the final velocity value. Alright, still don't have mass. Darn. Well, it's not so bad, because what you may notice here is, because both terms have mass, what we can do is we can divide both terms by mass. Now you can only do this if every single term in your equation has mass. Alright, but if it does, we can cancel it out of both sides, like we can do here, and mass is irrelevant in this case. Right? What really will start messing you up is if you have the spring formula, because the spring formula is 1/2 kx squared. There's no mass value involved in here. So if you have any spring components, you can no longer cancel mass, which is a little bit of a bummer, but it's just the way it goes. There'll be other ways to solve it. Alright, so back to blue, and let's do gravity times height initial, which is what we're looking for, by the way, is equal to 1/2 velocity final squared. If we're looking for height, let's just divide it out on this side and say height is equal to 1/2 velocity final squared divided by gravity. Alright, almost done this question. Let's plug in our numbers and finish it off. So height is equal to 1/2 velocity squared, so 3.75 meters per second. Square that one. Divide by 9.81 meters per second squared. And we end up finding that our initial height here, didn't put my little subscript on, is equal to, with 3 sig digs, 0.717 meters. That is how high this bob was dropped from. Alright, we can put a little arrow here. 0.717 meters. And that's all for example 1.